short so we can end on time for the reception. I'm very thankful that you are back here this time of the afternoon after probably so thank you for coming to the mini course. And I'm going to be talking about fusion categories. Maybe you saw the title that says something like new development. To be more concrete, maybe, and I don't know, maybe less flashy, about classification and constructions of fusion categories and modular categories. So sometimes I will be talking about modular categories because we know more about them, and sometimes about fusion categories. So my idea for the talks that could change a little bit depending how we go and how long it takes me is we will start by fixing some notation and introducing some examples and invariants that will help us later to give a sampler of classification results, or at least some of them, and maybe tomorrow I give some more. And then the idea is to start talking about different constructions for fusion, G-cross, modular categories, all these kind of ingredients, and say some new results or maybe some questions that are open about these kind of things. And tomorrow, again, maybe we'll say more classification and more constructions, and probably in the last hour I will say a little bit about what will happen if we go higher and we look about fusion 2 categories. I will not say a lot, but at least there is a classification result that I want to mention, and maybe say the ingredients and how you get some of them, but that depends a little bit on time. So a little bit about the motivation. Fusion categories or tensor categories maybe in general are natural hosts for symmetries. So it's kind of like classical symmetries were encoded by groups, but when you go quantum, for example, now that it's not enough, groups are not enough to encode the symmetries, and tensor categories are a good mathematical structure to encode them. And also, it was kind of a unifying language when in the 90s, I don't know, Drinfeld was studying quantum groups, and William was studying TQFTs in his way, and Von Jones was discovering the polynomial, the Jones polynomial. Then Reshetik and Durrell came with their notion that kind of unify all these things, and also Moore and Zeiger were working on things that define modular categories in the physical context. So it's like a nice unifying language, and they appear in many contexts in physics and in math, so I hope it's interesting for you. So at least I want to tell you a little bit what kind of problems we're thinking. In some sense, this theory is new. As I was telling you, a lot of things happened in the 90s that got people thinking again about monoidal categories, maybe with more structures, right? But it's kind of in the early stages, so we don't know that much about them. In particular, we don't have that many examples. We do have a bunch of examples that I will mention some, but are kind of families of examples and not that many new. Actually, subfactor theories at some point provided some exotic examples, but most of them now are related to some things or fit in certain families, so we would love to have more examples, especially exotic examples, to test our theories and to see what's going on. And one way to look for new examples is through classification, picking some invariant, fixing, like if you study groups, you can fix the order and try to study or try to say what are all the groups of certain order, right? So the same thing we can do with other invariants that I will be telling you about in the talk. And then the other thing we want to know is, if I have some fusion categories or modular categories, how can I construct new ones with these ones that I have, and maybe some extra stuff like an action or things like this. So constructions, from something that I know to hopefully something new. That's kind of some things that we are thinking about, among others, but that are some of them. So maybe let me say, I assume that most of you know what it's a tensor category, but I will say just the basics because I want to fix the notation and the language. Many people assume different things when they say tensor categories in the literature, so I will just say that kind of things. I'm not sure. If you don't see at some moment when I'm writing, tell me and I will use part of the board, and that's fine if I start writing too low. So for me, K will be also a field, algebraically closed and of characteristic 0. If this is confusing, think that K will be the complex numbers. That's fine for today. But just as a comment, there is a lot of things going on when you change the characteristic to a positive characteristic for the field. There is a lot of nice things going on in positive characteristic. I will not talk about that. And also, the things get much difficult when you drop the algebraically closed things. So for example, if instead of the complex I take R, things get much complicated. And John Sanford in his thesis developed a lot of the theory for fusion categories over non-algebraically closed fields. So it's interesting, it's harder, and we'll focus on this case, okay? So for me, a fusion category over K, or over the complex, will be is a category with a lot of structures and properties. So I want to have a K-linear abelian category that it's also monoidal. These are my two structures, but I will ask some properties. I will ask this category to be semi-simple, so every object will be decomposed as a finite sum of simples, and I will ask this to be finite. So I will say a smaller or a shorter thing of finiteness because I assume semi-simplicity already, but what it happens is that I have finitely many simples, and the home spaces in these categories that are vector spaces are of finite dimension. Think about these things. And then I want a rigid monoidal category, so I want all the objects to have left and right duals, and in this semi-simple finite case, actually they will be isomorphic, the left and right duals. And also what I want is kind of a compatibility condition. I have the monoidal unit, and I want that monoidal unit to be a simple object in this abelian sense. So the endomorphisms of one will be the complex numbers or the field, if we think. So here, many people, when they say tensor category, they think that it's symmetric or they have a braiding. I will not be assuming that. So if I drop semi-simple and finite, that's a tensor category for me. And if I say finite tensor category, it's because I'm assuming finitely many simples. So let's see some examples. Maybe let me fix some invariants, and then we will see some examples before I. So I think Xiao Wan was saying this idea that he wanted a periodic table for topological phases of matter, and since modular category models some of these topological phases, we do want a kind of a periodic table for modular categories. So which invariants would we include? Which invariants will be complete invariants? For now, we don't have any. At some point, we thought that modular data was that, but it's not, and maybe I will comment on that. So some invariants that we will be looking at in this talk. The first one is, I told you that I have simple objects in this category, and actually they are all what I need to describe all the other objects in my category. So I will have this set C, which I will have the simple objects up to isomorphisms. So isomorphism classes of simples. And this is a finite set because we assume finiteness and has the 1. And then another important invariant is the cardinality of this set, which is called the rank. And you will see that later we will be talking a lot about this invariant. So it's one way to control the size of the category somehow. The another thing that I said is my category is semi-simple. So if I tensor two objects, I will take simples because it's easier for writing. I tensor two objects, this will decompose as a direct sum of simples again. So basically I will be able to decompose it as a direct sum of my simples, but they will have certain multiplicity. Okay? So this will be, and this will be natural numbers or 0, and this collection of numbers will be the fusion rules. And this is also nice, because now if you think about this, it's like, in some sense, I'm doing some kind of higher dimensional linear algebra, right? I have an object, I can decompose it in this kind of basis, at least at the level of objects, if I forget for a little bit of my associativity and that. So what I can think is that given my object xi, what I'm looking at is how is the multiplication or left multiplication in the sense of tensor product by this object. And I could attach to this a matrix using this basis, if you think at the fusion ring level. And this matrix will be just Ni with coefficients given by these fusion rules. And what is nice is that because these are multiplicities, all these numbers are natural numbers, so or positive or zero, integer numbers that are positive or zero, and then Frobenius and Perron, the independently proved theorem that then this matrix admits a maximal non-negative eigenvalue. So I will write here another invariant that is related to all these, which is the Frobenius-Perron dimension. Again, I'm writing this for xi, but all these things that I said I could have writing for x. The only thing is that it would be a little bit more ugly how to write the coefficient. It would be a little different, but it will be the same definition. And this will be exactly what I was saying, the maximal non-negative eigenvalue of this matrix, Ni, which is always a real number, and it's always, as I said, non-negative, and actually for the basic element, for the elements in the basis, it's always positive. But if it were anything, it would be non-negative. And it really can be different values. You could have things that are not natural numbers, and we will discuss that in a little bit. And something else that I wanted to say, if this Frobenius-Perron dimension is very well behaved, I mean, I define it in the simples, but in particular, you could have defined it in any way for any x, but maybe, let me say, is additive, so it takes the direct, if I take the Frobenius-Perron dimension of the direct sum, it will take it to the sum of the dimensions. I will take it to the sum. Is multiplicative. Again, I'm using a little liberty on the words, so it takes the tensor product to the product. So if you give me the tensor product of two objects, the dimension will be the product of the dimensions. It takes one, the unit to one in the field, in the reals, and preserves dual. So this one I will write it. So the dual and the object have the same dimension. And maybe the last definition I wanted to write here, I will try not to change the word. So this is a very nice invariant. It's kind of powerful, and I will later tell you a little bit on how you can use this invariant for many things. But then using this dimension of the objects, we can define a dimension of the category, which is something that we desire, because we want to have different measures of the size of the category. And basically what we have been doing these last decades was trying to classify basically small fusion categories or fusion categories with some restrictions on the invariants. And to define this, or this definition is kind of similar to the notion for group theory. So in groups, this Frobenius, if you think about the representation of a group, that will be an example of a fusion category, rep G, for finite group. And here, this dimension will be just the dimension of the underlying vector space. So in that case, we do have natural numbers in the values of this Frobenius-Perron dimension. That's in a special case. And the square of the dimension of the irreducible representations of a group give you the order of the group. So that's something that we want to mimic. So what we will define this dimension as is as the sum of the square of the dimension of our singularities. So I already said that in groups you will get the order of the group. But maybe let me say some examples here now that I have some of the notation. I mean, maybe these two that I will mention at the beginning are not very exciting examples, but I will mention, because later I will mention, you have the category of vectors, finite dimensional vector spaces. Each time that I work with a vector space, underlying, I will want this vector space to be finite dimensional, otherwise I will not have rigidity. Because duals, as Jenny was explaining today, you have always the dual vector space. But you want this evaluation and co-evaluation that behave nicely, that you can straight up. And for that to exist, the vector space needs to be finite dimensional. So if I forget, always the groups will be finite and the vector spaces will be finite dimensional in here. So the category of vector spaces and also the category of super vector spaces are both fusion categories. This later will appear when we talk about other things probably. Then the category that I was just mentioning, the category of representations of a group. And there is a nice generalization of this example because the group can be thought, instead of looking at representations of the group, you could think of representation of the group algebra. But the group algebra has more structure on it. It's a Hopf algebra. And all the things that are nice here, they behave well when you have a Hopf algebra, if you know what it is. If not, I will mention Hopf algebra sometimes, but it will not be crucial in what I say. But for a finite dimensional, semi-simple Hopf algebra. And it can be also generalized even more to something called quasi-Hopf algebra that I will not talk now about. And maybe something related is this category, and this one will appear all the time. This category vec G omega, which is the category of G-graded finite dimensional vector spaces. And again, I will not mention the field anymore, think about the complex, but it's always over the same field that I'm defining. And here, this omega is something that determines the associativity constraint and this is a tricocycle of my group. So what I have are, if you think just as the abelian level without the tensor product for a moment, it's like you have one copy of vec, of the category of vector spaces, per element in your group. You have one copy in each element of the group. The group is grading your category. So you are decomposing any vector space that I give you as a direct sum of subspaces labeled by this element of the group. But then I need to know how to tensor them. And the rules, the fusion rules, are determined by the group algebra. So the simples in this category, and if I need to write something more, tell me and I can write it, but the simples are one-dimensional, because imagine that underlying is vector spaces, so I need to preserve what I know from vector spaces. So the simples are always one-dimensional vector spaces. But, I mean, in vec, I have only one choice, all of them are isomorphic, but here I don't, because I have one per group element. Because they will be like concentrated in that degree, and then all the other degrees will be 0. So how I multiply, or how I tensor two of these simples, I just tensor them with the group rule. And this omega, if you do the pentagon, if you try to write the pentagon for these simples, using Jules' lemma and all these things, you will see that the pentagon is equivalent to the tricocycle condition. So this is one nice example, because all these other examples, the associativity basically was the one of vector spaces, so kind of trivial. This one at least has a more exciting associativity, that's why I wanted to mention, and also because they appear a lot. This will be an important family. Okay? Then, okay, I wanted to mention two other things, maybe not much in detail, but a little bit. Okay, so the other examples that I wanted to mention are so-called near group categories. And I will not talk that much about this problem, but this problem is actually another problem that people think a lot in fusion and modular categories. Kind of categorification problem, because it's easier to find a fusion ring than a fusion category. You can give me a fusion ring, But in principle, I don't know if there is a fusion category that has that underlying fusion ring. And that's something interesting. We want to know when that happens. And for modular categories, it's the same with the S and the T matrix, which I haven't defined, but I will define in a little bit. So what are these near group categories? Are categories, fusion categories, with fusion ring of the following way. And I forgot to define one invariant. Great. So with the following kind of fusion ring. I want to have certain things. So these categories that I was describing here, the vec G omega, are the easiest to understand. In part because I told you that all the simple objects were these one-dimensional things. So maybe let me add one definition before giving this example, so it's later we'll use it a lot anyway. So I was defining here the irreducibles. There is a collection of irreducibles that it's a distinguished collection, which is called the invertible objects. So this will be the isomorphism classes of invertible objects. And if it's invertible, it's simple. I didn't tell you what it's invertible, so we will do that now. So what means to be invertible? It means that it has some kind of inverse for the tensor product. But the way to say that is that the evaluation and co-evaluation maps that we know that exist, and these are the ones that I defined this morning, are isomorphism. In principle, they are just maps, morphisms, but for the object to be invertible, I need these to be isomorphism. So what I'm saying is that X dual tensor X is isomorphic here via the evaluation to 1, and here via the co-evaluation to X tensor X dual. And this is the definition of invertible, but you can prove that this happens if and only if, and this is one of the things why the Frobenius-Perron dimension is useful, for example. This dimension is 1. Okay? And this set here has a group structure. It's a group with the tensor product as the product and the dual as the inverses. And the monoidal unit is the trivial, like the neutral element for the group. Why I wanted to explain that? So this category that I was saying here, the vec G omega, has all, in this category, happens that the group of invertibles is equal to the group of, not to the group, to the set of simple objects. I told you that one is included in the other, but in this case they are equal. So what they wanted here in this near group, that's why they are called near group. They are close to be these group categories, because I told you vec G omega has the same fusion rules than the group algebra. So this one is almost a group, but I will add one simple object. So the simple objects will be given by the group, and this will be the invertible object in the category, and one non-invertible. Okay? This forces a lot of things. If you want to have a fusion ring with this forces a lot of things. In particular, I mean, here the group elements will be following the group fusion rule. But one thing that happens is because I told you this thing about the invertibles and the dimension is multiplicative. There are some things that happen. If I tensor a simple object by an invertible, it's simple again. Tensoring by invertibles just permute the simple objects. So when I tensor X by any invertible, it will give me another simple object. And the dimension of X and this new object will not change, because the invertible has dimension 1. So it must be isomorphic to X. So what I'm saying is that these are all fixed. I want this to be the fusion ring coming from a fusion category. And these forces, first of all, the other thing that happens is that the dual need to be simple. And the only other, and the dual and the objects have the same dimension, so the dual will need to be itself. Maybe I will write it here. And then when you do X tensor X dual, which in this case is this fusion rule, these invertibles that fix x need to appear with multiplicity 1. It's something that needs to happen. So this was kind of required for these fusion rules. Otherwise, this seems a little bit weird, why it's like this. You could also make up this ring, but for having any chance of categorification, you want this. But there is an extra thing, because maybe that fusion rule seems familiar to you. You could have some multiplicity for this x. There is a very special family that it's the best. So in general, we don't know the complete categorification of these fusion rules. But Izumi studied a lot of these near group categories, and he gave a lot of some classification results and some restrictions on what you need for classification. I will say a little bit about that in a second, but there is a family that is very important. Maybe, let me say this. And it's a family when the x actually doesn't appear here, so m is equal to 0. That family is very special for many reasons. And one is that if you forget about this, you have some grading in your category. If you have m different from 0, it doesn't admit a non-trivial grading. If you have it, it gives you a set to grading. I will talk more about grading later, and I can mention this again. But in this case, it's also a very nice family because Tambari and Yamagami in the 90s, they classify or they check all the associativities by hand. They did this work, which is hard. They solve all the pentagons. And so there is a categorification result. For this to exist in Tambari and Yamagami, G must be abelian. So usually it's A. And the associativities go by some non-degenerate symmetric by character. And some, usually you encode it by the square root of the order of the group. But basically, because we're in the complex, that means that you have some sign going on. And this sign actually corresponds to something that is an invariant in the fusion categories. It's an important number. It's called the Frobenius-Schur indicator, if you know. And it's a Frobenius-Schur indicator of this non-invertible, of the x. But if not, it's that. And all the associativities are given. So if you have an abelian group and all these other two things, you have a Tambari-Yamagami category and vice versa. Okay? And we know when this is braided, when this is modular. One example of Tambari-Yamagami that maybe most of you are familiar is the Ising category when G is set 2. So that's a nice family, or it's a nice family in part because it has this. And I will just say, I will not write anything, but so the near group when M is different from 0, it's much harder. And so in the case when the dimension of this object is an integer, and the group is abelian, because in this case, in principle, it doesn't need to be abelian. For m equals 0, it's forced, but here, in principle, no. Etinghoff, Nikchik, and Ostrich classify them, and they are all Morita equivalent to the representations of some semi-direct product of cyclic groups. So they are more or less well understood. And then, when the dimension of this object is not integer, there is also classification by Izumi using more like operator algebraic methods, Kunz algebra and the tube algebra to construct the Drinfeld center. So it's very involved. And then when the group is abelian, but the dimension is not an integer, there are restrictions on what it needs to happen. The group needs to be an extra special group of certain order. So it's not totally classified yet, and it's an actually important problem because most of these subfactors, exotic examples, come from quantum groups or near group categories. And so it's interesting family. It's also a good family to compute. So maybe other things that I will be adding, I will add more structure into my categories now. For example, so what I will add now is a braiding. So I will be working with braided fusion categories, which we already hear the definition of a braiding today. It's just this family of natural isomorphisms that make my tensor product commutative, and I want this to be in a coherent way, so I want two hexagon axioms to happen. And they are very useful. They are related to Yang-Baxter solutions of Yang-Baxter, braid group representation, so they have many things. And in particular, I will be studying some special braid diffusion categories. So for that, I will introduce some, let's say that I call this B, and I will have the braid into this C. So I want to study a special subcategory of this braided diffusion category. Basically, what I want to know is how far my braided diffusion category is from being symmetric. So that's what this will encode. So this will be all the objects in B. So this is the full subcategory generated by this, such that C of Yx. So I will usually call this the square of the braiding because it's what makes sense to do twice. And now this, so this was going from X tensor Y. I changed the order with one of them. And then I changed the order again, right? So I ended in the same place. So now it makes sense to ask when this is the identity. And that's what I will be asking. And I want this for any other object. Maybe let's write this, the full category generated by this. So this is in particular itself a symmetric subcategory of. So this is a symmetric subcategory of B. Maybe I should have said what it means to be symmetric. It means basically this, that for every object I have this condition, that the inverse and the braid are the same. So the extreme cases, maybe I will delete this. So there are some extreme cases with this. This is a subcategory. We could forget for a minute that it's symmetric, but this is a subcategory, right? So one option is that the subcategory is actually everything. And in this case is when B is called symmetric. And there is a lot of work on symmetric fusion categories. I will tell you about that in a second. Not much, but I will tell you something. And the other extreme case, it's big as possible. So the other case is as small as possible. So as small as possible, this subcategory always has the unit. You can prove that the unit is there, and so all the things generated by the unit are there. So that's the smallest that you can go. The full abelian subcategory generated by the unit is just a copy of the vector space, finite dimensional vector spaces. And in this case, the category is called non-degenerate. And this basically, I will tell you the definition later, but this is basically being modular, up to having a ribbon structures, which Jenny more or less defined today in the morning. I will define it slightly different, but it's the same, but I will use a different notation, but it's the same thing. So B non-degenerate plus ribbon will be modular. So that's kind of one of the important things that I will look at. I will just mention this because sometimes it's useful. And I might say something about classification. One other potential case is the category of supervector spaces, because it's also symmetric. It's another potential case. And it's an important case, and it's called, in this generality, just slightly degenerate. But again, if you have ribbon structure, is supermodular, and maybe you have here about supermodular categories. They are also important, and there have been a lot of studies. So I will just say something about symmetrics, so you see the difference maybe between the two extreme cases and how much we know, and also because I want to say something that is going on and it's interesting, but I will not. And I will say that, and then we will take a break. It's a good point for a break after that. So maybe let me say this. So the theorem is the following, and this is the theorem of Deligne. These symmetric fusion categories that hypothesis of the field. I will write them again because otherwise things get very wrong. So you see is a symmetric fusion, and here it's important, but also the linear theorems tell you what happened for symmetric finite tensor categories. So, but I will say just fusion. Then we know how they look. And I was giving you some examples of things that are symmetric, like vector spaces and super vector spaces, but there is other category that is very friendly and it's symmetric, and it's rep G. If you do the braiding in rep G being the flip, just the flip, that's actually a map in that category because the action is diagonal. So if you interchange, it doesn't happen anything when you do the action before or after doing the braiding, the flip. And actually that's almost, it's not all, but almost all the examples is that or super representations of a group. So what is this? So G is a finite group. Z is a central element in my group. And the order of this element is at most 2. If it's 1, you get just rep G, and if not, you can get super stuff. Like this one that is rep Z2 with the sign doing the braiding. Instead of having the regular braiding, you have some braiding determined by some sign that comes from this, from looking at this central element. Okay? So if you see, for fusion categories that are symmetric, we have a complete classification. And the natural question in part could be, do we have something like this for modular category? And the answer is no, and that's why the mini course is going on. It's the opposite. We don't have any such a strong theorem, so it's totally opposite. And the last thing I want to say is that here, this is very, very important. If I don't have characteristic 0, things can go very different. In particular, there are a family called Berlinde categories. And you need to be careful because I know that sometimes some quantum groups categories are called Berlinde categories. These are some semi-simplification of some quantum groups or some categories coming from SL2. But also you can think that in characteristic P, the cyclic group, when you look at the representations, is not longer semi-simple. ZP, if you look at rep ZP, is not longer semi-simple in characteristic P, and what you do is a process of semi-simplification, and what you get are some categories that have fusion rules similar to Berlinde fusion rules, and that's why it's very, very different, and there is a lot of things going on. This is a very hot topic, but I don't know how much interest is for physics. Maybe we will break here and we come back in, Constant, it suggested 3 minutes. Let's aim for that. I don't know if that will work. Or how long break? No, the break, Constant. It's early. I started 4:30. Okay, no, sorry. We can go further and then I will do another stop. Okay, great. I thought that we... No, okay, perfect. So I will tell you a little bit about modular. So as I said, modular is basically the definition that I gave plus ribbon. And why this ribbon is important? Because it will buy me a lot of stuff. I will be able to get some nice matrices out of this ribbon structure. So let me tell you what's the ribbon structure. Again, it's basically a rephrasing of this morning, but I will do it in that way because it's a little easier for me. So let's say that I have C, maybe B, a braided fusion category. So what will be a ribbon structure? What I will be adding is some kind of twist. So what this will let me is a family of natural isomorphisms between X and Z for every object. But of course, here I have a lot of structure already. I want this twist, this I will call the twist, to play well with my structure. So what that means, the first thing that I have is the tensor product. So remember when we have the braid, I told you, I have 2 hexagons. That hexagons came from thinking what happens if one of the 2 sides of the braid is, the input is a tensor product. how can I describe it in terms of the individual braids? I will do something similar here. Something that you could dream or not is that this is a kind of a tensor map. It's not, you don't require this. You will adjust this by the braid. And what about the braid? I told you my favorite thing is this square of the braiding. So we will adjust by that. It doesn't need to be equal, but it needs to be equal to this composition. And maybe you have seen this interchange and it's fine with the naturality. You can interchange things. So this is the condition. There is something else that we will require because of duality. And we will ask that this is the dual map. Okay? So we will ask for these two. Why this is nice? So this is the definition that I'm giving you of ribbon, but actually it's the same as having a spherical fusion category, which is related to the pivotal structure. It's a pivotal structure that gives me traces that behave nice, that are the same left or right. So we could recover from here, or we can use the pivotal structure to get a trace for in the space of endomorphisms of X. So if I have an endomorphism of X, I will be able to take the trace of it. That's what it's buying me. And that's why I will be able to write two matrices. One of them I find it easier to write in this way, and I will do it in this way, but otherwise you could think in the other way. This map is an isomorphism from X to X. So now, if we fix for a second in the simples, as I was saying, or maybe I mentioned before when I was talking about G-graded vector spaces, the Schur's lemma holds because I have this abelian structure, this direct sum and all these things that happen. So I have Schur's lemma. What means that if I have a simple object and I have an isomorphism from it to itself, this map needs to be a multiple of the identity, a non-zero multiple, because actually I want this to be an isomorphism. So I will call this theta I to make it easier. And this theta I will be some non-zero element in the field. So with these elements, what I will do is I want to have two matrices. These two matrices will be R times R. R was the rank of my category. So the size will be given basically like what we did with the fusion rules, that I had matrices where the columns were basically indexed by the simples. I pick the color, I pick the i's from 0 to R minus 1, but the idea is that the simples are giving you entries. So this T matrix will be a diagonal matrix with the diagonals having the twist of the simples. And the S matrix is a little bit more complicated, but we will use my favorite thing again. No, I'm kidding. We will use the trace of, so I want to define it in the label ij. And what I will do is I will use the square of the braiding again, and I will do there are many ways to define, not many, but there are some ways. Not everybody takes the dual here. It's fine if you don't take the dual because it's a relabeling. The dual is another simple. I will take it because I will mention something about some things, and that I think that's the better interpretation, but it's fine. So now I have these two matrices, and maybe you ask, okay, why this is so exciting? There are very nice properties about this matrix in the modular case. What is the modular case? As I told you, so maybe let me write it. So now here we will have our definition, and maybe out of usage I will write MTC for modular category, and it's because for a long time we say modular tensor category, but maybe now we should say tensor category. There's a lot of study going on in non-semi-simple modular categories, but just in case I write, I'm assuming semi-simple, so unless I say something. But the modular fusion category is a non-degenerate ribbon fusion category. So if you have a ribbon fusion category, ribbon is extra structure. I'm giving you an extra thing that are these twists. But the non-degeneracy is just a property. You check, I give you the ribbon category, you check what is the thing here, which I didn't tell you the name and I will tell you in a second. And you check if it's back or not. If it's back, it's modular. If not, it's something else. It's a pre-modular, yes.
I had a question. Don't you usually have two traces, left and right?
That's what I said. Ribbon, because of these things here, insurance, because if I had pivotal only, it will be left or right. But I said that actually ribbon is equivalent in this setting to spherical. Spherical means that left and right are the same. It's like, and it's because I'm asking for both. I said I used the pivotal structure. Maybe I should have said spherical, but yeah. So this will be modular for me. And this thing here that I didn't give the name, this has the 2 because before there was the other center, which is the external center. Maybe you know about it, the Dreamfeld center. So they picked this notation, the center 2, I guess. And it's inside, and it's called the Muger center, or the symmetric center, or the transparent center, just in case you read different things for you to know. So symmetric is more or less obvious because it's measuring how far. Muger, because Muger studied this. Transparent is because these objects are considered transparent for the braiding. Basically, you are braiding 2 times and you can make it the identity. So you can transparent the braiding.
Sorry, could you please push up the board?
Yes, sorry. This one?
Yeah.
Yes.
Or maybe like interchange.
Yes, everybody will need to use. Let me. Okay, so maybe. Let me see what I want to say about this. Okay, so this. Okay, so maybe I was so excited about these 2 matrices. What about them? So one thing is that the S matrix. So if you have a pre-modular category, which is a ribbon category, so maybe if I say pre-modular, I'm just saying ribbon, in case I change the language. But so in this case, modular, which in principle I define it with this Muger center being trivial, happens if and only if this S matrix that I defined, that you see it related to the square of the braiding, so there should be some relation. And yeah, modularity can be measured in this case using the S matrix, and the S matrix needs to be non-degenerate, need to be an invertible matrix. That notion is valid always, that's why I say non-degenerate and all that. It's also interesting sometimes when you don't have the ribbon structure, but for ribbon categories, when you have this matrix, you can measure modularity out of there. And maybe, let me see if I want to say something now or give examples. Okay, S and T matrices satisfies a lot of things, a lot of nice things, and they are called the modular data. I will tell you a little bit about what is the nice things that they satisfy, and then maybe I will give examples. Too many things. Okay, so something that are nice about this S&T matrix is that they give rise to a projective representation of the modular group SL2 set. Okay? And so basically we send the generators to something related to the S matrix. Maybe let's send it to the S matrix for now, of the modular group, and this gives a projective representation. Sorry? Okay. So that's nice, and in some sense, maybe that's why they are called modular categories. I'm not 100% sure, but they give rise to representations of the modular group. And this has been key because there has been studied about how the representations of the modular group behave. And then when you want to classify modular categories, maybe in low rank is fine, but when the rank goes higher, it gets very, very hard. Using just S&T or some other invariants, it's not enough, and going to the representations of the modular group has been key, at least on the approaches that people have used. I don't know if there are others, but the higher low rank has been achieved using this path. So it's very important. Maybe something else to say. This T matrix, you have some T matrix, it's a diagonal matrix. One important result by BAFA is that the order of this matrix is finite. So in particular, all these twists that we were looking at, all the twists of the simple objects are root of unity. Okay? So the entries of this T matrix all live in some cyclotomic field, and it was proved that you can do a similar thing with the entries of the S matrix. So actually my category, some of the things I'm saying very vaguely, so don't worry, has attached some nice group that is called the Galois group of the category, and it's the Galois group that you get when you look at the field that you can get adding the entries of the S matrix. And it's the same as if you add S and T. You can check that it's the same. So this is another important thing that you can attach to your modular category. I got a little derailed from the S and T because I remember this, but the S matrix is a symmetric matrix. You can detect self-duality of objects by finding real columns in your S matrix, so they have a lot of information. The first row or column of the S matrix is measuring some important invariant also, that is called the quantum dimension of the objects. So the first row or column, because it's symmetric, will have the quantum dimension of each of the objects. The quantum dimension is a dimension that I didn't define because I will not use much, that it's defined using the trace instead of the Frobenius-Perron that was using the fusion rules. Okay? So that are some things. And because we have this ribbon structure, and as I was saying at the beginning, that I mentioned the Jones polynomial and all these things, there are links and not invariants related to this. So the T is related to the untwist, and the S matrix is related to the Hopf link. And it's kind of like that, why I wanted to put the duals there. Maybe I'm wrong, so I don't know. But this element basically gives you the Hopf link, and you need to divide by the dimension, the square root of the dimension of the category, or something like this. So there is some normalization, but you can recover the Hopf link color by I and J, like we were doing today. Let me see if I want to say something else about invariant. Something important is that for a long time, I told you, we want this periodic table of categories, modular categories in particular, because they have more structure. The definition seems harder, but then it's easier to study them because we have a lot of more things. In particular, all these things that I told you give you number theoretical tools to do things. So for a long time, it was believed that these pair of matrices that need to satisfy a lot of things, some of them are in code secretly here that I will not say, but there are some relations that they need to satisfy. They were a complete invariant. What that means, if you give me two modular categories with the same S and T, they must be equivalent as ribbon categories. That was people thought for a while, and that's not true. And the contrary example was not that terrible, strange. It's just that shows how sometimes we think that we understand very well some examples, and we understand them in a theoretical way, but not in all the details. So maybe let me give you examples, and I will tell you the family of examples that we can look. So let me tell you some examples of modular categories now. Some of them I will use the previous one that we talked about and try to tell you what you need to adapt for that. So Beck is always modular because there is no more going on. And SBEC is never modular, it's super modular, as you maybe saw. That's the other class that I defined. But another class that I defined before was this Beck G omega, right? I told you about Beck G omega and how important they are as an example. That are kind of one of the two examples we use. So one example related to this is Beck AQ. So what is this notation? A is a group as we had before, so what I'm doing here, finite dimensional graded vector spaces. But I told you the tensor product is determined by the group, the product in the group. So if I have any hope to have a braided category, I need that group to be abelian because I want commutativity. So I need to be abelian. And the associativity was determined by a 3 cocycle. So now I want something that let me determine the associativity and the braid. So there is something called abelian 3 cocycle, which I will not go on, but it's something. So if you have one of these, that will be that will determine your associativity and your braid. But all that can be encoded in some quadratic form. So if I have a quadratic form, I will secretly have these two ingredients that will give me the associativity and the braiding. But now I still want non-degeneracy, so I will ask for non-degenerate quadratic form. And actually the twist is also determined by this Q. Okay. Then other family of examples, maybe it's the one that many people is familiar with or not, it's quantum group categories. So we start with semi-simple algebras. And what I will look at is the enveloping algebra. So I will have now an algebra that we can do. And now we will, and this is kind of Greenfeld wave, right? He wanted to quantize, I mean, I don't know if it's exactly, but I mean, this idea that he wanted to quantize, he wanted a Hopf algebra structure, so we can do the UQG. And now we can look at the representations of this. But in principle, this will not behave well as I want, in the sense that I would like, and here Q for me will be a root of unity. I would like finite number of simples. Many times I don't have that. I want semi-simple. So what I need to do is I need to do some kind of purification. I need to quotient by certain things, tilting modules, or do some kind of semi-simplification process, and things will work well for certain root of unities. That depends a little bit on the data for G, okay, to get modular. But that's one of the biggest, these are very big sources of examples. Then, I mean, I talk about Hopf algebras. Again, if you don't know Hopf algebras, it's fine. It's not that I will use it a lot, but since maybe some people know. And I mentioned before, for this, what I will need to add is, to have a braiding, I need a quasi-triangular structure. So I want something that let me, and this quasi-triangular structure is something called an R matrix that lets you make the braid. And then what I want this Hopf algebra is to be factorizable for the quasi-triangular structure to be non-degenerate, not degenerate. And then I need some kind of ribbon element also going on to have the ribbon structure. Otherwise, I have only non-degenerate. Maybe let me say two examples that are kind of out of this. I talk about Tambari-Yamagami. Tambari-Yamagami is a fusion category. It's only braided when the group is an elementary abelian 2 group. That means that it's Z2 times Z2 times Z2 times Z2. The only case that admits a braiding is when you have a group like that. And it's well studied how many braidings and what happens. The only case when Tambari-Yamagami is modular is the one that we mentioned, is Ising. So Ising is an example. So Tambari-Yamagami with Z2 here. And it's only Tambari-Yamagami that it's modular. There is another interesting category, which I mean it's one of these quantum group categories, but Fibonacci, which is very nice, rank 2, only the unit and one extra object, and the dimension of that object is the golden radio. So you can see that we have nice, here we have a square root of 2 dimension for one of the simples, that's the Frobenius-Perron dimension, and here we have the golden radio. So there can be some interesting stuff. And then other family of examples kind of coming from here, and from groups, there is something that maybe you have heard about, that it's the double of the group. The double of a group, it's a Hopf algebra, and it's always factorizable. And even you can twist it by a cocycle, and you also get this. They are all modular. And also the double of a Hopf algebra is also a factorizable Hopf algebra always. And maybe, because I told you that I wanted to talk later about constructions, let me tell you one inspiration to go to constructions, and let me also tell you this about the modular data, and then we can go maybe now to break. These, I mean, they are examples from Hopf algebra, but they are examples also from a well-known constructions in fusion categories. These are center of one of the categories that I told you that are very important, this vec G omega, and this is the center of class H. And the Drinfeld center is a famous construction that if you give it a pivotal fusion category, it gives you back a modular fusion category. If you give it any fusion category, it gives you a non-degenerate braided fusion category, but if you give pivotal, it will buy you the ribbon structure. So if you see these examples seem like constructed by hand, they constructed these nice Hopf algebra structures that are on Hopf algebra that are factorizable, but actually they come from this more general. So it's interesting to study constructions. And also this counterexample to the modular data conjecture was given by Miñar and Schauenburg a couple of years ago, and it was actually looking at certain twisted doubles of groups. I want to say correctly which size was the smallest. So this, so maybe the group is here. You have a semi-direct product of set P and set Q for P dividing Q minus 1. And here, this semi-direct product has some N. Doesn't matter. It has some options. So we could consider these. And there will be different representatives of cocycles that I can take, one per each of these N, basically. And this can also be looked, as I said, as the center of some fusion category. A lot of the time when we say, oh, we have a category like this one, it's well understood and we stop there. I will say this when I talk about classification. It's one of the things that we think we understand. So it was kind of funny that this was a counterexample, at least for me, because it's like, oh, supposedly we understand them well, but we didn't realize at the beginning that they were what my collaborator Colin Delany called modular isotopes. What means that? In equivalent modular categories with the same modular data. The thing is that you can change these, and there are, so for, okay, these are modular, so for these to be modular isotopes, we need to be bigger than 3. The smallest of these is when P is 5 and Q is 11, and the rank of that category is 49. So you have 49 simple, so they are big categories. The matrices are 49 to 49, so they are hard to work with, right? So in that case, this N goes from 0 to pi minus 1. So it's like you have always N of these categories, and you want to know how many of them are in equivalence, how many of them have the same modular data. They proved that for Miñar and Schauenburg, proved that for P equal 5 and Q equal 11, there are 3 sets of modular data, but these are all in equivalent, so but 5 in equivalent modular categories. So there need to be some with the same modular data. There are actually one with the trivial cocycle that it's by itself, and then 2 and 2. There are 3 pairs of kind of modular isotopes in some sense. But in some sense, this for me was funny because we usually stop a lot of time when we get here. And I will tell you next after the break why. And later, maybe when we get to constructions, I will also tell you some insights, because after this happened, people start studying this. As I told you, S and T are 2 links and not invariants, are the Hopf link and twist. So you could look at that. But after that happened, people start studying, okay, what other nodes or links we can look that distinguish at least this family. can we find some complete invariants? So people studied other things like the Borromean rings and some other things, and they found that they distinguish these families. But you want to know for any modular category. These are very particular examples. So with one of our constructions, we try to give light. And something that was interesting is that the problem was, as you can maybe perceive from here, from the associativity even before the center. It was something more at the level of what of these initial categories were non-equivalent at that level that then translate here, but the modular data was equivalent. But I don't know, you had a question?
Yeah. So, for example, when G is SL2, just SL2, then its representation category doesn't have a finitely simple object.
No, that's why I said we need to take this purification.
Purification.
I call it purification. It's you need to do a quotient
truncated
and you need to truncate. Yeah, you need to do tilting modules or semi-simplify or you need to do one of these tricks or truncate to get a final. Yeah, that's what I wrote. When I wrote this line here is that you need to do something to make it look nice because in principle this will not. You have infinitely many, you could have other things happening, yeah. But for certain roots of unities, depending on the G and some things attached to the G, after you do this, you will be modular. You will be in the modular and usually unitary. There are a paper by Eric Rowan that studied that well and tell you which roots of unity you can take. Any other question before the break? Okay, so let's take a break, 5 minutes and come back. Or 3 minutes, so it's 5 minutes and we start as 500. No, yeah, 3 times.